Hello and welcome. Hello, UArt. That's what I said on the chat. I don't know why. Anyway, I would love to hear from you if you can see me and hear me. And welcome to another session of Raspberry Pi Pico hacking or emulating. That's it. Okay, let me switch to share my screen while I wait for to see on your chat that you can see and hear me. And welcome on this stream number 11 already. Let's see, where were we last time? So last time we had this joyous moment at the very end of the stream where we let's see if it still works, where we did npm start and we have seen the light. Or wait a second, we've seen a lot of output. That's not a light, but wait, I have a solution. We just want to see the UART output without all the debugging prints. And yeah, okay, so we had this moment of joy where we ran the program and we have seen hello UART. It worked. AB hello UART. So yeah, so hi Che, good to see you again, and Steve, great. So yeah, that was last time, and I think it was great. For me, it was great to achieve this milestone where we can run this program from beginning to end. And the first thing I want to do, you can see that hello UART is much bigger than it used to be, because last time we compiled it with debugging symbols. So we are actually running the debugging version without compiler optimizations, and I want to just revert to the version that we had before. That version has no it does have compiler optimizations. So let's just run that as a sanity to make sure that it even runs without optimizations. Let's fingers crossed. Yes. So yeah, so you don't so it runs with or without compiler optimizations. And I think we can start with discussing what's next. So I have a few things in mind, and feel free to suggest in the chat anything that comes to mind. But first of all, I would love to release an alpha version. We already got enough instructions. Actually, sorry, I'm a bit distracted today, but that's the way I am. I would love to see how many instructions we have implemented so far. So we can do it probably by counting how many else if we have. Let's start with opcode. So we have 64 of those plus this one, so 65 instructions. So with 65 instructions, more or less, maybe I've missed something. Yeah, it seems like I got them all. So we have implemented 65 instructions, and yeah, we can release the first minimal instruction set that is required to run hello UART. We have probably missed a few instructions. I don't know how many there are. I never, if you want, you can count in the datasheet and let me know how many we are missing to complete the instruction set. But we have 65 instructions, and I think it can be useful, or at least beginning of useful. So that's one thing. And the other thing I think we really need to make this more useful or more functional is GPIO, so we can run Blink. And we had like hacky GPIO. Maybe there is like still a code here somewhere. Yep, that listens to yeah, to writes to one of the GPIO registers, and it I think, yeah, it's in the SIO address space. And it tells you if the pins are high or low. So we can make this more generic, create some abstraction that wraps this, and let the user attach a virtual LED, or print the status of the GPIO in console log. Also GPIO, we want input. Maybe not today, but I think it's pretty useful to have GPIO in and out. Then another thing we need is timers, because if you want something like Blink to work accurately or to work at all, we need to implement timers. These are the mechanisms that let the software running on a microcontroller know when a certain amount of times has passed. Another thing, I mentioned it many times before, is the PIO, and for this one we actually got a customer already. So I went to this. So I forgot to tell you about this last time. There is this new, or for me it was new, project called Arduino Pico, and it's some guy that created Arduino core for the Raspberry Pi Pico, so you can compile your code with the Arduino libraries like digital read and digital write. And I spent a week playing with that. I wanted to see if I can hook it to the Arduino CLI, so I tried that. Actually, I think it was just after the stream last week. So I tried it and got this error. So I sent him a pull request with a proposed fix, and we started chatting. And he said he has a lot of ideas that he would love to implement with the PIO, but debugging PIO code is really difficult or impossible. And we started chatting, and it appears like he would really love if we can. Once we have PIO in the emulator, if you could use that to debug his code for the Arduino Pico core. So I think that's really cool. We already got the first customer for PIO. So I think it's a good reason to put it on the list of the things that we want to do. And then I don't know how to prioritize everything, but I also would love to get MicroPython or CircuitPython running in the emulator. I think that would be super cool. And to make things even more overwhelming, there is one more thing that we need if you want to get MicroPython and CircuitPython working. At least one more thing. Maybe I'm missing something, but that's USB, because they have REPLs that by default they work over USB. UART over USB. I think that's called CDC. That's the serial ports over USB. So that's another thing we would need to, or we should probably have that, because I guess. Also the Arduino core use that as the serial backend by default, so it doesn't print to the. It's much more user friendly to use the USB for that, instead of requiring the user to connect to the physical UART with another UART adapter or something like that. So I think this is actually like these are the three things that we'll do first, and then once we have those, we can decide if we want to focus on PIO and make that that guy over there, this Earl, I don't know how to pronounce that, so make him super happy, or just go with MicroPython, CircuitPython, or maybe we'll just get lucky and they will work out of the box, who knows. Cool. So let's get started. Like, we have a lot of things to do. Let's start with releasing an alpha version. So how do we do that? We have that code that works here, sort of, with a lot of debug prints. We need to tidy it up. So first of all, let's delete files that are not really related, all those debug logs, files that are not versioned. There is also an output.txt. Where is that output file? Maybe inside. Where did you go, output? Oh, I deleted it. Okay, cool. And then we definitely don't need to release the hex file for Blink and hello UART. So I'm going to remove them from Git. And let's add them to the, let's move them here. Okay, and then, oh, I think they were never in Git from the first place, so that's better. I'm pretty sure they were inside. Is it like not updating? Oh yeah, it's closed, yes. So yeah, so we will stage the deletion of them, and we will add them to git ignore, so they won't be part of the repo anymore. And yeah, let's do that. So now they should, oh, star.hex. So now they should, yep, disappear from this list. Cool. And we still have them if we want to play around with them. Another thing, we need to export some kind of API to the users. So we want to create a file that will be the main entry point for this package. This is going to be a library that people can just use in their code. And we are going to, for now, we are just going to export this RP2040 class from RP2040. And I think for most users that would be the API that they would use. They would just create an instance of this class, and then I think we have this execute method, so they will call it, and they will probably have to attach some code that would listen to UART outputs. Cool. So the other thing we want to do is to get rid of all these debug logs. Yeah, if we need them, we can add them again later, but you know, with some kind of flag or something like that. This should be probably console.warn, just to make sure we don't miss them. I think let's run it again and see. Execute, where are you? Or, oh, we called it run blink. Yeah, it doesn't run blink, but it's called run blink. All right, so okay, so first of all, I would move that file probably out of src. It's going to be like some kind of example or demo, but first I want to see if we got rid of all of this. We can remove this. Yeah, this is spamming the console. Okay. Yep. And then, yeah, this is like, I think we don't need to print when we hit a breakpoint. To do raise hard fault exception. Yeah, I think we can just comment it out for now. Okay, cool. Now it runs beginning to end, not to end. And then we still have those rights to undefined address. That doesn't look very good. And who prints that someone wrote? Is it like, oh, this is like unhandled SAO rights. Okay, we'll probably refactor that part. Okay, let's see. Yeah, it's much less spammy. Which instructions are not implemented yet? They are not important because nobody cared, but those right to undefined addresses, is it like, oh, undefined is just the string. I thought it will try to write to an address whose value was undefined. Okay, so this is just writes to places to memory we still haven't implemented. So yeah, let's leave these errors still, because it probably means we are missing something. Cool. Right. And we have this index file that exports the RP2040 class. Now, the next thing I think we can do, let's remove this. So right now we have this constructor, and it gets this hex, but hex files aren't really common in Raspberry Pi Pico. UF2 files are more common. And I think we can leave it up to the user to decide how to load the code. And if you take a look at the tests that we wrote, we actually, in our tests, we just pass an empty string. So I think that shouldn't be a concern for the library. So it shouldn't have to deal with loading hex. If somebody wants, they can load their hex themselves. It shouldn't be part of the services that this library offers. We don't need those constants anymore, I guess, if they are commented out. Yeah, it's that time when we tidy up all the code that we created. And okay, and now we can update the tests so they don't, they don't use that constructor. Cool. And then I think we can move run link to, let's create a new demo directory. And we can move it here, run link. So it's not part of the release, it's just a demo. And then we can just move the Intel hex here as well. And then we can just load hex into mcu.flash, and eventually we'll probably change this to just load UF2. I think they are already generated when we build stuff with the Pico SDK. We already get the UF2, and I created a library a few weeks ago that lets you access UF2 from read UF2 files from JavaScript or TypeScript, so we could use that to read them. And then we don't need that probably anymore. We don't want to start from, don't know even what we did there, just like a basic demo, or maybe we can just call mcu.execute. Cool. Okay, and then let's change the start script to run this demo. So it's now inside demo and yarn start or npm start, doesn't matter. Yeah, it still works even though we moved and shifted things around. Another thing I would probably change right now, the boot ROM is hard coded. And I know they have 2 boot ROM versions, and I read that they are not compatible. So some of the like you can't build one binary that works with both boot ROMs or something like that. I think I heard that in this related to CircuitPython. But if you know differently, let me know. Anyway, I think we can let, for now, we can let the user provide a boot ROM and not like hard code this specific boot ROM revision. So let's also move this code to the demo and create an API for that. Right now, where do we use the boot ROM? Oh, it just reads it. So read only boot ROM is just an empty array of 16 kilobytes, and then we will just read from this.boot ROM, and maybe yeah, we can move all of those initialization sequences into a reset method. So there will also be a way for the user to just reset the microcontroller to the initial state. And then we also like access the boot ROM below here. So we can do something like const boot ROM is taken from this. So this works. And what else do we have? Oh. Let's add a method load boot ROM that does, first of all, int 8 array, this.bootrom.set bootrom data, and then after loading the bootrom, it resets. Cool. So now the API has changed a bit. Oh, we need to bootrom, take it from this. Cool. And now we can update the demo code to load the bootrom. So mcu.load bootrom, and bootrom, just maybe we'll name it bootrom b1 because that's b1 revision of the bootrom. Bootrom b1. Oh, it's UN32 array. Cool. Let's fix that. Otherwise, we'll have bugs because the code assumes it's a 32 array. So it should be 32 array, and the size should be, that's the number of elements. It should be a fourth of the original number. Cool. Let's run the code and see if it still works. Yes, perfect. So we haven't, and let's of course run the tests and make sure we haven't broken anything. They are running. Cool. All right. Thank you. One test is failing. Which one? Oh, this one. Yeah, it's testing the initialization, and we remove that. So for that test, we can load bootrom and give it bootrom. Actually, we don't need the entire bootrom. We can just, we know which entries it loads. So we can just give it those two numbers. I think these are like the first two numbers in the array, if I'm not mistaken. And EE, not 32, 3. Cool. So dummy bootrom and test passes. Cool. Okay, so I think the last thing I want to do is to make this GDB server more generic. So instead of like having it as a standalone program that just runs the server, I would just make it some sort of API that you can call in your program to implement this GDB server. So we can, the good thing about GDB is that it's pretty stateless. But yeah, we can probably create a class called class GDB server, and that has a constructor that takes RP2040. And then just move those. This function is stateless. It can be even not part of the class. Like we can even export it in case somebody wants to implement their own like transport and not use this default transport of why do we need a file system? We don't. So yeah, so then we can do something like GDB server. So it takes, this is read only, and then we don't need this. This is the responsibility of the user program. And then we can just do something like a GDB server create. Maybe we'll change it to and let's make the port configurable, but we'll have a default of 333, I think it was. Yep. Cool. So 333. Yeah, so we already have the socket server, and then this.socket server.listen with the port that we got. Maybe let's make it read-only as well, so it will be available as a property of this class. and then we definitely don't need this, but I'm actually going to make it part of this blink. So we will use this API in a second in the demo program, so we can check it works. Cool, and then we need to listen for connections, and basically these.socket server.onConnections on connection. No, this is the API. Socket this.handle connection with socket, and let's move this into a class method, handle connection, that gets a socket. What's the type of the socket? Socket. Okay, and then it can do all sort of things with the RP2040. We need to import socket not from here, from net. Okay, and then actually, instead of doing this dot 3 everywhere, we can just do RP2040 equals this. And yeah, I think it's still, oh yeah. Oh, so this method also assumes that it has, so we can probably make it a class method, and then maybe we can like do, let's start with making it a class method. So that would be just process GDB message and const RP2040 equals this. Cool. And then we return this dot process GDB message. Cool. So we have this implementation, and we need to export this, otherwise nobody will be able to use it. Okay, I think one more thing we can probably do is to, no, I wouldn't do it now. I was thinking maybe to create like two versions, like one which is with just process GDB method, so you can create your own transport instead of using the socket server. But I think that for this version, maybe we'll call it GDB TCP server. And then in the future, if you want, we can create like a more generic GDB server that doesn't have this TCP part and can do, like, gives you your own hooks to send messages from GDB and get responses, like basically this, or maybe the code that you have here, like getting data from over some other kind of channel, which is not a socket, named pipe on Unix, for instance. But for now, this is good enough. And then we can also export this GDB TCP server as an API. So if somebody wants to use it, they can. But if they don't, like if they run it on a web browser, then they don't have this net and create server, and then they will just be able to import what they care about. Cool. So that would be, now we need to use that to make sure it still works. So import GDB. Actually, we can import them from just the src directory because they are exported by the index from. Actually, two, I'm thinking, yeah, we can probably configure it so that, no, we'll do this for now. I was thinking maybe configure it to point src to the package name, but I think it's just too much of a distraction for now. Okay, so and then we can GDB server is new GDB TCP server with the RB24, called it MCU, and port, and then we can say GDB listening on this port. Okay, let's start. And now we have like a combination. Before that we had like two different tools, one to run this maybe let's call it execute run emulator, yeah, or emulator run, yeah. Before that we had like these two versions, one that would just run the code and the other that would run the code and GDB server, and now we have this API, so it's super easy to switch between just commenting out 2 lines or making a command line flag or something like that would make this GDB server totally optional. So we changed it to emulator run. And by the way, if you have any suggestions about the names of the APIs or anything, feel free to let me know. Okay, this is running now. Let's try to run GDB multi-arc, whatever, target remote local WinHost. That's my Windows machine, 333. Trunk and register, that doesn't sound too good. GDB connected, GDB disconnected. Interesting. So, oh, maybe it doesn't know which architecture we are using because we haven't loaded an ELF file. Now, where do I get the ELF for this low UART? So, since last week, I actually moved all the Pico directory to the WSL partition, so everything runs faster. So that was inside the build UART, low UART, and then we need to copy the hex file because that's the version with the debugging. So if we want the symbols to match what we have, what we are running in the simulator, we should copy it, and then we can GDB multi-arc file, yes, whatever file, low UART.elf target. Oh, and let's restart this friend. Okay, and then target remote Windows 333. Ta-ta-dum. Yep. Okay, cool. So yeah, it seems like it stopped and GDB still talks to our code. So I think with that we are probably ready to. We have done some initial refactoring to make this more like a library and less like a bunch of code that we randomly hack together. There is like still a lot of stuff to refactor, and we'll do it over the next few weeks once we start implementing the peripherals. But we can say refactor prepare for 1.0 release. Cool. Or not 1.0, that would be 0.1 release or something like that. First alpha release, yep. Cool, so we have done this, and I hope everybody is happy with, or at least someone is happy with the API we are presenting here, but it's just an alpha, we can change it. All right, and now we need to make sure that we can build this code. So when we publish this code as a library on npm, we don't want to publish the TypeScript files because otherwise it will be challenging for users to consume them. We want to publish it as JavaScript files. So we are going to add a build step here, a build script that would just call the TypeScript compiler, npm run build. Now when we run it, we can see that it hopefully, it creates those files inside this, even though it compiled the demo and we don't want the demo to be a part of the release. So let me see. It's probably in the TypeScript config. We can specify root directory, which will be src. Okay, now if we npm build, it doesn't work. Let's see why. We probably need to tell it to look just under src when compiling the release version. But before that, another thing you probably notice that we have multiple versions of the files here. So before compiling, I want to install a package called rimraf that will allow us to just remove the directory, this directory before we build. So we always get a clean build. So now you should see it's removed, and since we have the error, it was created with the new files, but it also errored. Interesting. So we did run it, it did create the files, but it also errored probably when it got to this. No, it did. Interesting. All right, so we need to tell TSC to compile just files under the src directory. We can do that in tsconfig. It actually already complains about that. What does it say? Yep. So there is like include list that we can tell it to include everything under src. And is it happy now? Or maybe files? There are like two ways to tell it which files to compile. That way probably. Is it happy now? But I changed that. Okay, let's start the command line compiler again and see what happens. Still not happy. So maybe that should still be included. Okay, it was happy, and it just it created this with just the files under src. That's great. Another thing we want to do, we don't want to have those spec files in the output. We don't need them in the release, so we can exclude them. So we don't want you to compile them. Let's build and see that they are gone now. Yep, no spec files, just code files. And this is the JavaScript, like how it works through the TypeScript compiler, and you can see like it does some transformations. But this also means that users of TypeScript won't be really able to take advantage of the types in this package. They won't have this autocomplete and all of stuff, because this directory doesn't include anything that is TypeScript related, only the compiled JavaScript version. And for that, we can ask TypeScript to include a types file. So we say typings. I include, I don't remember. There is a way to tell it declarations. I think it's called declaration true. Let's see if that works. To tell it to create another set of file, those files that include all the types. So they have the types, and then there is the JS file with the code, and that's like a standard way to publish stuff on npm. But we are still not there. We are getting there. We also want to tell npm not to publish all the files there, which is the default, but rather to publish only the files inside dist. So we need to add a files section here and tell it we want to publish everything inside dist, but nothing else. As a matter of fact, it automatically includes the README and the license. That will be like what's going to be published with the package, everything inside dist and the README and the license. All right, and I think one final thing we can do, which will be helpful for the users, is to generate 2 versions of the code. So there are like 3 or 4 different ways for modules, like to define modules in JavaScript. There is the new standard, which is ECMAScript modules, and it's pretty much supported across the board now, but there are like still older versions of Node.js and other software that use this older way, which is CommonJS, which uses the require. So right now the best practice is actually to publish 2 versions of the code, one using the new syntax, which is what we're using here with export and import, and the other one is to use that older syntax that is also supported by, that's the default syntax for Node.js, like this require syntax. So I'm going to change the TypeScript configuration. So instead of outputting this inside dist, it will actually write it into a different directory, or it would write it into dist CJS, which is CommonJS, and then I'm going to run, so now it's inside dist CJS, so we have this version with require, and we are going to create another version by creating another tsconfig that inherits from the original tsconfig. So I think it extends tsconfig, and it will have slightly different options. So instead of like it will have two differences. No changes to this and that. So it will use yes next, which is the ECMAScript modules, and instead of like the default CommonJS, and it will write those files into a different directory. And now we can tell we can run tsc again. So tsc -p that's tsconfig.esm.json. I think -p tells it which config file to load. Let's see if that works, if I remember correctly. If not, we'll Google that. Tang. Ooh. Yeah, I think it worked because now it failed, so it probably have read this other file. Oh wait. Ew. What did they do? I think I removed all the data. Yeah, I edited the wrong file. That always happens. So let's revert those edits. And then the file tries to extend that itself, and it probably doesn't do anything. It probably doesn't work. Now, the right content in the right file. This one extends tsconfig, and tsconfig still has the default configuration. Okay, npm run build. Let's see if it works now. Yep. Okay, so now we have 2 versions, the ESM version and the CJS version. The CJS version uses this require stuff, and then the ESM version uses these imports and exports, just like we have in TypeScript. And the last thing, now it's, I think, the really last thing we need to do is just tell Node.js where is the entry point of the library. So there is like the main, which is the CommonJS version. So it's inside this CJS index. That's the entry point for the common version. And then there is like a way to specify the entry point ES modules, the entry point for the ES module version. And there is like a way to tell it how to do that. Hey Nekati, good to see you here. Yeah, there is like main. Oh, there is like, I remember there is a way to tell it which file is like a different file for just ES modules. Yeah, main. If we want to support both for tools that maybe for Webpack, entry point package.json modules, ES modules. Export the main entry point along with subpath. Is there any example? Yeah, so it seems like the exports can be used for that. So we can say that if somebody is just exporting the package, then it should read from this ESM index.js. And that would probably do the trick. So it would allow users to import it either as common JS modules or as exports. Let's just Google that real quick to see if other people are doing that. I haven't used that before. Main together package.json, or if any of you have experience with that, that would be cool. Otherwise, worst case, we'll publish a bogus. There is an example that sounds good. We'll publish a bogus module, and we can always publish a new version. That shouldn't be a problem. Okay, exports. No, that doesn't do this. Yeah, okay, so let's do that and hope for the best. And one last thing, we also need to tell it where to find the TypeScript definitions. So it will be able to do autocomplete and all that stuff. So that's done by the typings field. All right, so I think we have everything we need to do in order to release. So this CGS index, it exists, cool. This ESM index, cool. And this ESM index.d.es, cool. We can, double check that and debug. No, that. So yeah, the path is correct. The path is correct. And there are like ways to check packages before you publish them. But if you don't have any users, then you can publish whatever. And I think we are ready to publish the first version of this half-working Raspberry, or less than half-working Raspberry Pi Pico emulator. Let's see. So yeah, I already created a placeholder on npm. So if we go to npm.js rb2040.js, you can see there is like already a package just so nobody else gets the name before we do, or there used to be one. Let's see, rb2040.js. Build amazing things. Why they changed their homepage? Yeah, this is the package. Just published a placeholder version 0.0.0. You see, it has some downloads. Interesting. Somebody downloaded it. Okay, whatever. So for those who downloaded it, now you know it was useless, but now it's going to be a bit more useful. We can probably add more information in the README, but I think it's not really ready for public consumption anyway. So if anyone wants to use this package, they will just have to watch the live stream. So for now, we can just, I think, publish it as is. So we can set up release npm or one more thing. Yeah, I always forget that, but we also want to run this build script whenever we publish to npm. So we can define this pre-published script that will just run the build script. So whenever we npm publish this package, it will automatically build it. And I wanted to test the tests to see that they are still working after all of the changes. Yeah, they work. Cool. There is a console log here. Where is it coming from? Yeah, we don't need that. Go away. And then also the example program to see that if it still runs. Yep, it still runs. Cool. Everything is great. So setup release or scripts, npm scripts for release. All right, and now I think this is a great time to release this to the public. So there are like a few ways to release an npm package. In this now I will just do a very simple release, just npm publish. That's like the simplest way, but usually I use a command line tool called np, which also increments the version and does all sort of other fancy stuffs, running the test, making sure that creating tags, or maybe, yeah, let's use that. That's I want to keep the version. Let's keep it simple. Let's just npm publish and create a tag alone. We can in the future we'll use that cool tool np. So now we are uploading this first version to npm. First problem, we should have called it npm run build, not npm build. It's not really a problem because we ran the build a moment before publishing this package, but in the future it will be. So let's fix that. Npm run build. And before we commit that, let's just create a new tag for this release. So this is the repo, and we just created a first release. So create a new release. It just creates a tag on GitHub, F010, and initial alpha. Not very useful, but still impressive in my humble opinion. Cool. Now we also got the tag on GitHub, and as soon as we released, we already have a bug fix. We can fix pre-published script. I want to stage this, and let's go to npm and see if the version number has updated. No, not yet. They usually take a few minutes to update their website. But if I just go to an empty directory, let's create an empty directory, and now the directory, yes, it's empty, you can see. Now if I npm install rp2040.js, I can actually use that package. You can see it installed a new version, and I can do like require rp2040.js const rp2040, and it doesn't work. Cool. So yeah, probably Node is confused by the fact by the configuration of the module. like there is like way to tell it to use ES modules, but yeah, but probably including that exports maybe it should have been .mjs for ES modules. I'm not sure. I will have to spend some time reading about the proper way to do this kind of releases, or if one of you knows. Oh, by the way, thanks you, Stevan. I just saw your comment. If anyone knows how to set it up correctly so a Node.js can consume the version that it's happy about, that would be cool. Maybe there is like a flag that we need to tell Node.js ES modules. That's the problem with new technology. It's pretty new. Like you see, there is like this article is from last month. Yeah. Anyway, never mind. I will read about that later. I don't want to get into that. So we have a release. It's a bit tricky to use it from Node.js because Node doesn't like, it probably likes this syntax, but it doesn't expect it in a file that ends with .js, or we need to change something in the package.json. Oh, type module in package.json. Okay, that Tomasz said that. I hope I pronounced your name correctly. Let's try that. Why not? So type. But is there a way to support both? I would love if we. You know what? It's a new package. I don't care. But then maybe we don't even need to publish the CJS version. But anyway, let's first get it to work, and then we can remove the CJS version in a subsequent release. But yeah, now we can create the second release of this. Yeah, wow, that was fast. So I will run, maybe I have it installed globally now. I will now show you this cool tool that I love using, np. It probably won't run because we have uncommitted changes. So let's add type module to package JSON. Oh, committed. And let's see. It's still loading. Oh, in the consuming. Okay. Yeah, but I think it makes sense to let's Google that, to use type module. Yeah, that was here. Type module exports package.json to say that I'm a module as well, maybe. Yeah, I should probably read about that more. Type. Okay, let's try what you suggested, and if that works, we can skip this new release for now, and I will figure it out offline. So all right, let's try to create a package JSON here. So this is like the one that consumes our module, and then node, and then const, how did we call it? RB2040 equals require RB2040JS. No, that still doesn't work, even though maybe we need to, create a file here, index.js, import. Maybe we need to use the import syntax, and then it will be happy. RB. Okay. Node index. Yeah, name not found is a common JS module which may not support. Interesting. So when I tried to import it as a common.js module, it said, no, this is like, this is not, I don't know this syntax. Well, why do you have an export there? Because it tried to load this, but now when I'm importing it with import, it says this is a common.js module. So it seems like it's playing games with me. Interesting. I mean, I can try to do this, but that would be pretty dumb. It feels pretty dumb to do this. And then it doesn't like it anymore. Interesting. Oh, wait. Set type in the package.json. But I did set type. Maybe I didn't type module. No worries, Tomasz. That's cool. I mean, that's the reason we are here. We are trying stuff and see how bad is the JavaScript situation with ECMAScript modules. Anyway, so yeah, I think we'll leave this alone right now. I will just revert the last commit because I'm not sure it will fix anything adding this type module. Maybe exporting both TJS and ESM is not the best version for, you know what? Let's make it simple. Let's remove the ESM version for now. Like, we can still build it, but let's remove it from package.json from now. So it will, let's remove the last commit first. Reset soft head. Yep. And now we can just remove this exports thing. It's broken probably, and just leave the CJS for now. And we can, once we figure it out, we can add the ESM again. Once we find a way to make it happy, but for now let's just keep it a CJS, all good and working. Let's make the typing point to the same directory again. So release only CJS, or maybe set the entry or remove exports from package.json. It confuses Node.js, making the package unusable. All right, and now let's publish version number 2 or 0.1.1 with those new changes. And then hopefully somebody will be able to consume this package, which is still not super useful until we figure out a better way to support ESM modules, or maybe we decide that we don't want CJS and just ESM and just have to spend like an hour or so reading about this and understanding what's the best way to do this. So that's a patch version. And now this is the one of the ways to automate publishing packages to npm. It just makes a clean directory, runs everything in the test, and then it also creates the tag for us, so we don't have to create the tags in GitHub manually like we just did. Bumping version, publishing to npm, and voila, we published 2 versions in like 10 minutes or so. Pushing tags, and now it should open a new it opened a new window with a new version 0.1.1, and it has all the changelog here. So this is going to appear in the GitHub releases pages, so people can see what has changed between this version and this version. Cool. Maybe we'll change this to be V, just to be compatible with this one, which is also V. Then we'll remove that tag later, like this. Oh, but now it says this is the latest release. How can we, maybe if we just updating it will work. Maybe, maybe not. How do I tell it to make it the latest release? Not sure. And let's remove this tag. You can't remove this tag here. Never mind. Doesn't really matter. All right. Anyway, so coming back to here. Let's reinstall this RB2040.js and try to use it again. Maybe this time the new version will be better. Yeah, and then we can see we have the class, and we can of course create an instance, RP, and have all these things inside, all these members, and yeah, basically well, now we can like create a script that uses it and simulates, and I think I don't want to close everything, just this one, and yeah, it's published, it's there, people can start using it. Congratulations. But more importantly, we now have a way to automatically push new releases, so that's going to make it much more streamlined, and we'll probably push a release or two now, starting from now on in every session. All right, so now complete shift. Let's start implementing new stuff. So I think the next thing I want to try to do is the USB, and then we can probably go to GPIO. We had this list somewhere. Where did we have it at? Yep, this one. So we did this alpha version with 65 instructions. Yeah, let's where did we have that? Yeah, let's edit this release on GitHub. Ooh, wait a second. Yeah, I think this tag is like broken because the commit is, yeah, it's, we should delete this release. It's, something is broken here. And then this tag is not a good tag. And then we can make a release out of this tag, edit tag. Maybe we can change. Yeah, I find GitHub confusing. No, it did it again. It just created a new tag. I only wanted to change the existing tag, not to create a new one. Okay, let's remove this. How do I delete this release? That is not really a release. Delete. Okay, so we'll just let's make a new release from the old tag, or maybe I will just create a tag in the command line. I mean, there must be a way to rename tag. How do you rename a git tag? Git tag new old. Okay, so git tag v0101010. Oh, I need to delete that new tag because v010. Now I can, and then I need to push it somehow. Right, git push origin, that was v010. It's probably going to break somehow, but let's try that. Maybe it will work. So yeah, it just hangs. Okay. And what happens here? Oh, it worked. Yeah, now we have but now it points Ooh, yeah, how we delete this tag in GitHub. Okay, maybe there is a way to force push it. Maybe this will help. Push force. Push force. Push force. Force push. All right, it takes a lot of time, but it hadn't failed yet. Yes, so finally, I think we sorted this out. So now we can recreate the proper, the tags are now properly set. Who could imagine that it would take so long to just, rename a tag? Anyway, so that was initial alpha release. Not very usable, but still impressive in my humble opinion. Implements instructions. So that's ARM V6M. I mean, we say this is impressive, we need to back it up with some data. So this is the data. And some, I think that's enough for, Now we finally, it will probably say it's the latest release now. No, now everything is correct here. The order of the releases, the tag names, everything is fine. So now we can move on to what really matters, which is making this super cool simulator with USB and stuff. Cool. So back to the code, complete shift of mind. Let me see. So we had this we have this Pico examples repository, and we have I want to try to get USB to work. So for that, let's go to the examples, and there is a USB, hello USB, which is just using printf, just like serial over USB. And I guess, let's see, there is a difference. What's the difference? So it's the same code as hello serial. Actually, let's start with running hello serial. It's a shame we haven't run hello serial, which we ran hello uart. Okay, let's see if hello serial works. Maybe uart works, but serial doesn't. I think hello uart, did it use printf? No, it uses the uart function. So maybe printf still doesn't work. Let's see if printf works before we go and run to implement hello USB. So hello serial. I think we have this build. Pico examples, build hello. No, it's in hello world serial. And let's copy hello serial.hex to tcp/rb2040.js. Cool. And now let's try to run it. So let's emulator run. No longer run blink. Just try to run hello serial, which is obviously different than hello uart. Okay, npm start. And let's watch the wonders, or not. Let's see what happens. Oh, ooh. Okay. So the good news is that we get some output, but I don't think this is the output that we want to get. And panic, panic doesn't seem so fun. So it did print hello world. So printf works. That's good news. But then right after that, it had a bunch of missing instructions, and it panicked. But this is a good news, because now we have UART, so we can actually see the panic messages. Attempted to sleep inside exception handler. Use busy if you must. All right. It sounds like a riddle or something like that. But anyways, we have this working, but it's probably failing because we haven't implemented timers or something like that, and there is a slip there. Yeah, and this slip probably causes something to go wrong. So what do you say, timers or USB? Which should we do first? Let me know in the chat which one do you prefer, timers or USB? And meanwhile, I think we have some other work we can do, refactoring we can do to make our life easier. Because right now we have this sort of mechanism to set up read and write hooks on specific memory addresses, but I think it's going to get pretty complex once we start have multiple peripherals, and each one will have to set a bunch of read and write hooks, and that could easily get out of control. So I think last time we saw in the datasheet that there is some, I think it was here, there, I don't know. Yeah, like there is like each peripheral register block is allocated 4 KB of address space. So there's like some kind of order that we can exploit. So we can, instead of just letting peripherals hook to wherever, we can define a way for peripherals to get notified when somebody writes to one of those addresses, and we can also implement all those behaviors probably in a generic way, instead of having every peripheral implement those spatial write access rules. Cool. Yeah, and this narrow register writes memory mapped IO registers. Cool. So yeah, so meanwhile I will start doing this, and let me know in the chat if you have by the way, YouTube tells me there is a problem. There might be a problem with the stream. Do you see any problem with the stream? So let me know if you do. Anyway, I will start implementing like refactoring how peripherals work, and then we'll eventually need to get rid of all this stuff in the constructor and have something more organized. But let me know in the chat, meanwhile, if you prefer to focus on to start with USB or timers. Otherwise, I will have to choose, and I hate choosing. Cool. So I think what we want to do now is to have a list of peripherals. So, oh, thanks, Steve. A list of peripherals, so we can just or map of peripherals. So all the peripherals have that's the there was like a list of all the peripherals, I think. Okay, maybe 2 timers. Cool. So we'll start with timers. So there was this list of peripherals. Where was that? Yep. So there is like this list of peripherals, and we can already like each peripheral is has these 16 kilobyte blocks, and we can actually convert this into code. So like, yeah, create a list of peripherals, read only peripherals, and then have this into a code, and then let's just have a class that implements all those peripherals that we still haven't set up. So we can do something like that. There is like the base address, and it's just new unimplemented peripheral, and then we can have this class sort of oh, and we also need to include the or maybe have this yeah, and then we can also sort of include like make this class implement it, so it warns us whenever somebody is writing to an unimplemented peripheral. So we'll create this class in a moment, but now we have a map of peripherals. So it should be a map that maps the address into into the peripheral, and we have the name, so we will be able to print the name of any unimplemented peripheral access instead of just saying somebody wrote some value to a memory address we don't recognize. And then we basically don't need all these like zeros. We can just like have the higher bits of I mean, they are always zeros, so we can just have those. Now let's create a directory for peripherals, and we can create this unimplemented, or maybe just peripheral.es, unimplemented peripheral, and it has a constructor that takes protected RP2040, which is an instance of the RD2040 and read-only name. Cool. So we have these peripherals, and now it's a string, and now we need to import it here, right? And instead of for the UART, we already have the peripherals, so we can do I think we even created those here, so we can just do this.uart0, this.uart1, and we'll need them all to implement some kind of interface. So we will probably do that in a moment, but first of all, let's move the UART into the peripherals directory, and then we won't need those UART0 base and UART1 base, because that's something okay, we'll get to that in a moment, but that's something the RP2040 class will take care of, basically just giving us the relevant part of the address, so the peripherals don't have to worry about where they are mapped. They won't even need, or maybe we can just do like before, give them name UART0 and UART1. All right, and then let's create an interface for the peripherals. So we know that those peripherals, they can only handle there is this part where they handle they treat all writes as they were 32 bits in size. This makes our life easier. So offset and value. So each peripheral will have a write which has an offset, and then read uint32 which gets an offset and returns a number. And then for the unimplemented peripherals, write uint32 will just for now it will just warn us peripheral unimplemented peripheral write. So writing, okay, so this implements peripheral. It's one peripheral, not multiple. So this has offset and value, 2 offset to string 16 and value. Cool. And then same goes for read, read uint32 offset number, and then oh, we can also say which peripheral it is to make this even more useful. So this is read from, and we'll just return all f's if we don't recognize this address. I think we already do this. And now we can start using it. So we don't need those anymore. I think they don't exist anymore. And then, yeah, we have UART0, UART1. And then when we are writing, so when we are reading, we can check if const peripheral is this dot peripherals, and then we just take the address and remove that was 3 zeros, so that was 12 bits. We will remove 12 bits. Oh, and we need to tell TypeScript that we can index it with any number. Otherwise, it would try to ensure that we only index it with one of those numbers. And it's a peripheral. Cool. So now TypeScript should be happy when we try to index it with arbitrary numbers. And then if peripheral, if we found the peripheral, then we just return this dot peripheral dot read with the address. And basically the same goes for write, but with writing we have this yeah, for writing that was 12 bits or 16 bits. How many bits did we yeah, I think that was 12 bits that we removed. It was here. Yeah, 3 zeros is 12 bits. For writing, we probably want to implement this behavior of like, first of all, if you write less than 8, if you write like 8 or 16, like this one, like writing that allows you to XOR set or clear bits. But maybe we'll worry about that later, not now, because I'm not sure yet if it should be a part of the write unit or something the peripherals should have control over. But let's first of all implement writing to peripheral. So if peripheral, if we have a peripheral, then just write to this peripheral. Address and value. And when we are doing narrow writes, we'll also need to take care of this thing, like repeating the value instead of doing other stuff. We discussed it last time. So if we write A5, it should write A5 4 times. Or if we write, what was that, food, it should write food, food. Cool. So let's do that. So writing uint16. So if we have a peripheral, then we do something a bit different. And maybe this is not a correct behavior, like reading it and just updating the specific byte. I'm not sure if this is, I think this might be the correct behavior for the RAM, but obviously not for the peripherals because the datasheet says otherwise. So in this case, we just write it to the aligned address. Oh, wait a moment. I sense a bug. Yeah, we should, when we are writing or reading from the peripheral, we should only, we should mask the bits. So just give it the lower bits of the address. So it gets a relative address and not absolute address, because it doesn't care about the absolute address, or it shouldn't. So this is reading and then writing, and then we can do the same here. So we want to use the aligned address, so we don't care about those bits. They should always be 0. And then we need to replicate the value 4 times. So basically it's value and ff, or yeah, or value or this shifted by 16 or this shifted by 24. I think I got it right. Can't tell. Doesn't seem like I did anything wrong. Okay, and then the same thing goes with the right uint 16. Whenever we have this right, if this is a peripheral, then just take the value and copy it twice. All right, cool. So now we also implemented that part of narrow IO rights, hopefully correctly. We'll test it in a moment. Yeah, let's test it. Oh, wait a second. First of all, let's make sure that the code compiles. UART is still not implementing the peripheral interface, so we say implements peripheral. Now, instead of using those hooks, it can actually implement right uint 32, offset, number, value, number, and read uint 32, offset, number. And then if we are reading, we can do switch. And if we have this one, this register, we need to return 0. And same goes for the right. Switch offset. And for right, if we have this one, the data register probably, then we are doing this. All right, cool. Yeah, we need to return something otherwise, so let's return all Fs. Or you know what, actually, yeah, it's no longer a base address, it's name. Read only name string. Cool. Yeah, actually I like this behavior of unimplemented peripheral that prints stuff, so maybe we can change it to be logging peripheral and then export class unimplemented peripheral is just a logging peripheral, and then we can say that UART is extends logging peripheral. I think implement should come after extends. Cool. And then we don't need the stuff in the constructor. It's already handled by the logging peripheral. And then we can just, if we don't recognize the offset, we can just return super read uint 32 offset. And same with write. So if we have the default, if it doesn't match, then we can just super.write uint 32 offset value, and that would also print like the message that says, hey, somebody wrote to an address we don't recognize. Cool. So I think the next thing I want to do is to write some tests, I guess, for this narrow rights behavior. So let's do it. All right, we can, yeah, create a new section here, describe, how did we call it, narrow IO register rights. So it's a new set of tests. It's not testing execute instruction. And then we create an instance of each should replicate for 8-bit values 4 times, and then we create a RP2040 and we say RP2040 write uint 8, and let's add a new peripheral just for testing, a mock peripheral dot peripherals at let's say 10 just for testing equals write uint 32. That's a way to define a mock function, or maybe we'll and also read uint 32. It's a mock function, so that's one way to go. Another way to go about it, which I actually, no, that's good. That's cool. Maybe just make this one to make it easier to use it later in the assertion part. Cool. So this is a peripheral. It has those two functions. And then we just write to this address, let's say 10, 1, 2, 3. And we are writing the value 5, 3, 4. So we expect it to just take 3, 4 and replicate it 3 times. So we expect peripheral we expect write uint to be called with this address, just without the lower bit, so aligned address. And then we expect, yeah, just 34, 34, 34. And it didn't pass, so what did we do wrong? First of all, we can see that it was called, which is a good thing. Let's just focus on this and RB2040, no, not the spec file, RB2040 itself. Cool. And then let's go to the write uint 8. So yeah, it found the peripheral and it called write uint. Let's see what values it called it with. There is a way to show the value, show value. Yeah, 288. Is that this one? 288? Why doesn't it show it as an hexadecimal value? Yeah, so this one was correct, and then the other one was probably wrong. Oh yeah. Of course, I had to shift left, not shift right. That's a bug. So thank you, test, for finding it. And now it's green. Great. We probably have the same bug with the 16-bit write, so we'll have to fix that. Maybe 4 times and twice. All right. And then if we are writing 16 to this address with 4, 3, 4, 5, 6, 7, 8, we expect it to be called with the same address, but 5, 6, 7, 8, 5, 6, 7, 8, and yes, we have the same bug here, obviously. So because we copy pasted, we needed to shift left. Cool, and it passes. Now, Che Guevara's asks in the chat about the atomic operation implementation. Yeah, that's we haven't implemented it, but it would be a good idea to. I don't know if at some point we will implement it. We will have to. Probably somebody uses it, but I'm not really sure where I should implement it right now. If it should be. If it's better be part of the peripheral and like the base class will take care of this, or it should be part of this class. Since we don't really know who is using it, what I'm going to do here is if offset is greater than this, no, it's greater than, yeah, oh, yeah. I see another bug already. Anyway, if the offset is greater than this, then we'll also add another warning. Unimplemented atomic write to peripheral. Now, I'm not sure how read should work, but let's add a warning as well, just to make sure. Read, I think, from peripheral in the atomic operation region. I'm not sure how this should be, the read should work. We should look for it in the datasheet. But for now, let's just not worry about that and get these warnings displayed. And I already found another bug while doing this. We were a bit too aggressive with the bit shifts. I mean, where is that? RB2040. So peripheral. So we cleared 12 bits, but actually 12 bits, or wait a second. Yeah. So we want 16 kilobytes, so that's 14 bit. Yeah, each peripheral has 4 kilobytes. So that's the 12 bits, but then there are like 4 regions. So we need to shift it by 14 and not by 12. So let's make a test case for that, actually, and then fix it. Because we love tests. RB2040, cool. And thanks, Chef, for the comment. Otherwise, I would have probably missed that. Okay, so that's atomic IO register writes, and maybe we can just IO register writes, put them under the same category. It should support atomic IO register write addresses. So it shouldn't support the write operations themselves, just making sure that the addresses are mapped to the peripherals. And if we try now, we can see that if we change it to this, let's do write unit 32, 1, 2, 3, 1, 2, 3. Yeah. And it it doesn't do alignment, I guess. Yeah. So we can see that if we change it to this value, then we would expect this to be called with that address, which is still in the peripheral space, but it's the atomic IO register. But it doesn't because of that issue with the shift. So let's fix that. Write unit 32. Same goes for reading, even though I'm not sure if what reading should do in those cases. We need to console the datasheet. But right now, let's just redirect it to the peripheral so we get a warning and we know we need to do something about that if that happens. So let's fix that by changing the shifts first of all. Should be shifted by 14, and then those bitwise should be we should take more bits. Peripheral dot write, so taking more bits here and also here, and there was another one with here. Cool. And now the test should have passed, but it doesn't. Why doesn't it pass yet? It's not called yet. Interesting. Let's focus on this one and see what we missed this time. So right, we're in 32 and okay. Yeah, it doesn't get here. All right. Yeah, shifting by 14 wasn't a good call because then it won't match those. Yeah, so what I'm going to do instead of shifting by 14, I'm going to move this to a different function. Otherwise, it starts to get out of control. Let's call it find peripheral address number, and then it will return the peripheral for us. So it basically does this, it returns this shifted by 12, and then I'm going to clear the lowest 3 bits, or we can do it like that. can shift it 14 and then shift it back 2. Cool. And then instead of this, I can just find peripheral at the address. Cool. And now the test is green. Perfect. Another bug found and solved. I like that. Cool. Okay, so I think at that point we have something basic that should handle peripherals, and let's see if that works. So we expect the code to still run and print stuff and still panic like before, but now we can see that we have those messages. Attempted to sleep. So yeah, it works now with the new peripheral class. So what did we change here? Just load a different file, but yeah, refactor, create peripheral class, or yeah, it's more like interface. There are like a few classes already. Cool. So that's a nice refactor, and now we can use that to as a basis for implementing things like the timers. Or no, we haven't tested it, but yeah, you can see that we have those unimplemented. There is an unimplemented atomic write to a peripheral. Let's see which. Yeah, I guess it's the UART, because there are like writes to the UART, but yeah, now we can see when this happens, like just like we did now, to peripheral, and then this name, and we don't need all spaces here. Yeah, now we can see when we have timer based. Yeah, now we can see that somebody is trying to access the timers and probably set them up, and we can see like all the suddenly this output make a lot more sense to me, because suddenly we can see that what's going on here. Like instead of like writing to invalid or unknown memory address, we see names that mean something. We know that somebody wrote to UART, and we have the address of the register, which is cool. This sounds, yeah, this is an atomic write to the UART. So yeah, this is helpful. And now let's try to take a look at the timers. What's going on? First of all, there is like this missing instruction. There are like a bunch of them. So let's try to connect with GDB and see what's going on. We have GDB already. We just need to load a different file. Hello world cd. That's the serial one. And then we can file hello serial.elf. Target remote Windows 333. Debugging, and then we want to take a look what's there. Disassemble this address, cc4, that's the function. And where is cc4? adcsc. No, that's cd4. Where was cc4? uxth, twice uxth. Does it complain about uxth? cc4, cc2, cc6, cc8, cca. Yeah, it complains about a bunch of instructions here. Yeah. Okay, so probably still not done with the instructions. Let's see. Where are we, by the way? We are in this function lmul, probably multiplying numbers. So we probably haven't had to multiply numbers so far. Where are we in the... Oh, we didn't set a breakpoint there. But yeah, we can see that we died inside sleep until. Maybe we can fix that. not sure. Yeah, if get current exception, probably get current exception returns true, and it shouldn't return true because we don't have an exception as far as I can tell. That's another thing we should look into probably next week, doing interrupts and exceptions. So that's another thing that peripherals should be able to do, interrupts. Okay. TUI disable. But let's map the missing instruction. That was what we wanted to do. So we had one here, UXTH, UXTH. We don't have UXTH. I guess it's super similar to UXTB. What does it do to UXTH? UXTH, unsigned extend half word. So we have UXTB and UXTH, and yeah, it should be pretty straightforward. We can probably do it in a minute or so, or like 5 minutes. Cool. And then so we have this UXTH. There is a way to tell it. I think this AS, yeah, to show the opcode as well. So yeah, UXTH. And then I guess the other complaints are about muls, because I see a lot of muls here. Let's see, we don't have muls probably. Yeah, we also miss the muls instruction. So multiplies to register values. Cool, doesn't sound too complicated as well. So there is also muls. And is there anything else here? So let's see. We have CB0, CB2, CB0 moles, CB2 is also moles. CBA, CBC, CBA, UXTH, moles, then, and that's it. CBA, yeah. There is CC4, 6, 8, and A. CC4, UXTH, UXTH, moles. Yeah, it's probably those two instructions that are coming out as missing instructions. And then I think there was another one. Yeah, this one. What's there? What's here? A32. What's it? A32. A32 CMP. Interesting. So are we missing that instruction as well? That's CMP with mediate and CMP with register. CMP, we have CMP with register. So did I get the address wrong or something like that? Again, so 1001A32, 1001A32 CMP. Interesting. Yeah, are there, oh, wait a moment. There are two encodings for it. What's the difference? There is like this N LSRS. What about it? I think we have LSRS. I remember we suffered a lot with LSRS. So yeah, we have it. But where did you spot it? But yeah, but there is like two encodings of oh, there is like, what is this N doing? I think this N tells it to use the upper registers. Yeah, the number is like, so like this bit is probably prepended to those register numbers. Oh, interesting. So yeah, so we have like CMP, but then how comes it's R12 and R6? This is like, it's not this one, and it doesn't need, it's not this one. It doesn't make sense. I mean, it can't be. It can't be. I mean, you can't compare those two registers with either of. Is there another CMP? Or is the datasheet wrong? Yeah, okay. What did we do in the implementation? CMP register. So yeah, we assume that this bit is 0. Oh, now I see. What is n? Wait a moment. N must be 0 probably. RM is 4 bits, so that could fit the like the R12. But then Rn, Guess not both means that one of them is from R0 and the other can, I mean from this range, and the other can be from this range. Otherwise, I don't really get it, how it works. So I guess it depends on the value of n, and this is like a specific case. This is a private case of this, or am I missing something? Like, I think what it says is that if this is 1, then this must be 0. That's complex. Anyway, so that's the third instruction we are still missing. So yeah. That's one thing we need to do, those instructions. And then let's try to take a look at the timers and see, maybe we probably need those instructions for the timers, but let's see what else do we need for the timer peripheral. So first of all, we can create the timers peripheral instead of pretending it's unimplemented. Let's move it from unimplemented to implemented. So timer base, that's the timer peripheral. That was the one, right? It says timer. It said timer. Timer. Pads, reset base. Yeah, timer base and reset space as well. But yeah, timer base is like it's writing there or reading there from there when maybe the missing compare instruction is why it figured out we have this panic, because compare returned the wrong value. It didn't compare. Cool. But let's start with the timer based peripheral. So let's call it timer.ts, and then it just love copy pasting. So rp timer. Cool. And then for now we don't need to implement those, I guess. I mean, yeah, let's just have the base implementation that calls the super. Okay, cool. We don't need those. We don't need this. Does the UART need this import? It doesn't. It's useless here. All right. Yeah, so we have the timer, we have this change in the UART, and some fixes in the peripheral base class. But yeah, the timer is the important thing here. And then let's change the RP2040 to use the timer instead of this unimplemented peripheral, RP timer. Cool. And the purpose of unimplemented peripheral is to eventually go away as we implement all of those peripherals. There are not too many, but there is still some work here. Cool. And let's see what's going on with the timer then. Let's stop this and run it in with a grep so we can see who is using the timers. Oh, we need to redirect the errors to the standard output. Oh, and thanks Che Guevara's for the comment about CMP, that one register has to be R8 plus. The datasheet is like, yeah, not easy. And we consider like a few writes and reads from the timer base. So let's try to see what's going on there. I guess this is like trying to read the current time, so it knows how to set the delay. So let's take a look at the timer registers, peripherals, timer registers, and we have 24, that was right, yeah. So this returns the time, high and low. And how does that work? Oh, and we had, so let's create constants for those first. Before we dive into how they work, because timers, these is like the essence of the, so this is 24 of the timer, the high and low. That's 28, cool. And then these are read-only registers, so we don't need to care about writing to them. They are only readable, which makes sense. And there is probably an overview that tells us what happens. So this is a single 16 4-bit counter incrementing once per microsecond with the reference generated by the watch in the watchdog. Okay. But it counts microseconds. So this is pretty cool, because this means we can just count microseconds. And there is a node API. So this counter per registers reads from the 32-bit bus. Okay. So, oh, you can write the time and read the time. There are like registers for writing the time and registers for reading the time. Cool. These pairs are used by accessing the low L followed by the high register H. So always use the L then H. So reading the L latches the value. So the adder. Oh, there is like a way to read the row time and with latching or without latching. Technically, programmers, timers, exposing. Okay, so people says don't write the timer, so we can probably assume nobody is writing there, but let's check the address. It's 0 and 4. Do we see any writes there? No. Somebody is writing to 20 and to 38. What's it? 20 and 38. It's 20. We have armed. Ooh. Probably setting one of the alarms. All right, that's a 20, and 38 is interrupt enabled. So I think we may need to implement interrupts sooner than later. Because it's setting the timer to armed and then trying to probably enable interrupts. Yeah, we are writing 8 to those registers. So let's see what 8 means. So armed, writing 8s. So it arms an alarm, but it didn't configure the alarm, or so it seems. We haven't seen a write to the alarm register. So maybe It's armed, but it doesn't have value. Interesting. And then the interrupt enable probably enables interrupt for that register, for that timer. That's 38 int e. Yeah, so it enables alarm 3. And I see those constants repeating all the time. So let's create, well, they will probably be useful. So like those bits who control the alarms, we'll probably need them. Cool. 0, 1, 2, 3. Cool. All right. Actually, I like this timer. It seems pretty simple timer. I remember, just for the reference, was it here? Yeah. The timers for the AVR, when I implemented the AVR simulator, that was a nightmare. Like, this is like, it starts here on page 102 and it finishes, actually it's not that many pages, but they have like so many different options and so many different configurations and way of working. It took me forever to implement those, like, and there is 8-bit timer and 16-bit timers, and to go all through all these diagrams and understand all the nuances. And here, this is like super nice. Like, it has a single counter and 4 alarms, and when there is a match, there is an interrupt. That's nice. Yeah. Programmers module, reading the time. Cool. So yeah, we can implement reading the time probably. Switch offset. Oh, and there are like 2 ways to reading the time. So there is like the raw registers. So this is the high part of time. Actually, no, we can't really do that because in JavaScript shifts are always 32 bits. So shifting by, if we had the time and we shifted by 32 bits, it means we are going to return, so JavaScript doesn't really have integer it has number, which is double precision integer. It's not really a number. So if we are doing shifts, it's always in 32 bits integer. So the number is first converted into, the double number is converted into an integer. So doing this is the equivalent of doing this, which means don't shift. So we need to just, another way to go about it would be to divide it by 2 by 32 and then just, floor the result. And we still need to obtain the time, but let's assume that we have it for now. And then timer AWL, the low part is just time. That would that should convert it to an integer, or no, just we can bitwise end it with. Yep. And this is reviewing, so it should be unsigned. So yeah, I think just like shifting it by 0 should do the trick. Let's just make sure this works. Like, let's say we have a really big number, and then we lose 5, and then we shift it by 0, and we get 5. Yeah, it gets us the lower 32 bits. And now we need to find the time. So for that, first of all, there are like 2 more registers that they mentioned there. Where was that? Timer HR and LR, which aren't latched. So let's implement that. Case. So LR is C. Const timer LR C. And H is probably before that. HR. That's at 8. So if the offset is timer HR, then we return this. If the offset is timer LR, we return this. Now, if we are reading from, these are like the non-latched version, but if we are reading from the latched version, it means that whenever we read from this value is updated. So we need to store it in some temporary register. Latched time high is a number that equals 0, and then whenever we read from LR, we just do this this.latch time high. We sort of we just store the value and then we return the low part, just like in reading the row register, and then here we just return this.latch time high. So sort of like caching the time or saving it aside, so the user get a consistent point of time. It can't change while if you are reading just these registers, then if you are reading L and it's at the top of the 32 bits boundary, and then 1 microsecond, like there is a tick, then this will be increment, and this should be 0, but you read it before reading this, so you got sort of inconsistent, incorrect time. So that's why they use this latching. Cool. So now we just need to figure out what the current time is, and there are a bunch of ways to do it. We want a microsecond resolution, and there is a way to do it in JavaScript. The annoying thing is that it's I don't think there is a consistent way. Microsecond resolution time JavaScript. I think there is like a different API for the browser and for Node.js, but let's see if I'm wrong. I hope to be wrong. Google Chrome does not support. Okay. Yeah, so there is this API, Window Performance Now, which returns high resolution time, but it's only in has microseconds, milliseconds. Nobody is sure about it. It's pretty horrible. Yeah, and then there is like another one that's probably in Node.js. So there are like a few ways to get high resolution time. I didn't know about HR time. Yeah. Oh, there is like a version that returns big int. Interesting. Yeah. And then I think for ease of use, we will just use the performance API for now. And there is like a way to use it in Node.js. So I will just create a utility that helps us with this. Time get current microseconds, and then we can do if type of performance. So we will write code that works whether it's Node.js or the browser. If it's not undefined, then we are running in the browser. So we return performance.now, and that I think that returns nodocs. That returns milliseconds. So we need to multiply it. Microseconds, no, milliseconds, I think, measured in milliseconds. Yeah. So we need to multiply it by 1000 to get microseconds. And then we'll just round it. No, we will floor it to make sure it's an integer number. And then otherwise, we will use the Node.js, which is perfull.performance.now. It's basically the same API, but it's not available globally. Yeah. So this code will let us get the current time sort of accurately, both in the web browser and in Node. And then we can just do something like const time equals to get current microseconds. And this should probably work as long as nobody is setting the time. If somebody would have set a time, then we would need to store the offset. But it says, they said it's discouraged to set a time. So I guess we can, where was that? Yeah, we can probably get rid of all those unrelated stuff. Go away, go away, go away. We don't need you. I would love to do it for you, but today we won't get to the GPIO. We don't need this. No, no, no. Yeah, I think that's enough. Okay, so the datasheet said that writing to the timer is discouraged, so we can skip that for now. And I think other than the interrupt, we got the very basic, the very essence of the timer implemented. We still haven't tested it, but not sure how we could, I mean, we can probably mock this. No, I think that wouldn't be worth it. But yeah, you can now see that the reads, they don't show up here. So we implemented that. And then we can probably yeah, this is the atomic write. So it already happens. We already have to deal with that. But I wonder what's up with the panic. Do we still have it? We probably do, because we probably still don't have that. Yeah, there is still a panic. We don't have that compare instruction that we need. Yeah, but first of all, let's commit what we have now. A skeleton of a timer. So I need that one, right? Okay, fit RB2040, a skeleton of a timer. Or fit timer. Yeah, that's, we can say it's a skeleton of a timer. It's not a complete timer, but it already sort of returns the time, untested, unknown if it works. But I mean, it's pretty straightforward code, so it will probably work. Just a moment before we commit, I want to make sure. So to go over the changes real quick. So probably formatting this. Yeah, adding the parentheses, that's fine. And removing an import and adding this, cool. All right, so we have that. Yeah, so let's try to implement that, to fix that CMP instruction, so we can hopefully get past that panic. So we need to, first of all, assembler. Oh, we don't have assembler for the CMP instruction. It was probably one of the first one that we implemented, so it's not even assembled. That would be RD2040 CMP. Yeah, we haven't done this, and we can see there is no version to compare to registers. So let's create one. I will skip the assembler for now, but if anyone feels like sending a pull request later, that would be cool to add like the assembler for this. So CMP this, and this is actually 40. Oh, is it this way or that way? I think it's this way, because I hope it's this way. Cool. Let's try to decode it, and then we see if we got it right or we need to reverse it. And then we can say that R12, there is no R12. We probably called it something else, IP or something like that, right? IP, yes. So IP is 60 and R6 is 56, and then the result should be just like here, because these are like the same, R5, R0, R12, R6. Maybe we should say it's IP 12 with R6. Cool, and now let's implement that, shall we? CMP register. So there are like two ways to do CMP register. That's one way. And then we can probably go to the datasheet and see how we match that one. Oh, that's a different prefix. I get it. So yeah, so that's different encoding. So we'll just do another one. So there is like this one, and there is this like this CMP register encoding T2. Okay, cool. Okay, and then the prefix is like this. So copy paste. I didn't really miss doing instructions. I hoped we finished with them, but we still have a bunch more. Okay, so this one, and then we have RM, which is, oh, okay, so this is like 8. And let's focus on this test. Yeah, we can see it's getting into the if. That's cool. So probably we got the opcode right. And then RM is like shifted by 3. And it's 4 bits. And RN is like opcode and shifted by 7. No, shifted by 4, because we want to move this into this position. And only this bit, or that one. And then I think the rest should be, why did I mess up? Yeah, the rest should be the same. Yes, it's green. Cool. So we may have fixed that unimplemented instruction. Let's try and see if we still get a panic, or do we get somewhere else? Ooh, yes, still get a panic, and there is still an instruction that wasn't implemented, but where was that? It doesn't say where. Oh, that's after the panic, so we don't really care. Yeah, but yeah, we can see that I think it stopped complaining about that missing instruction, specifically the compare one. We can, you know, just we know the opcode, so we can see if it that was the opcode, so we can see it doesn't appear here. So apparently adding that instruction didn't make it happier. We still have the panic. I hope that would help. But we can see that there is another instruction here, 26FE. That's the boot room. Let's see what's there. Why doesn't it work? It's running, right? Oh, yeah, I run it inside WSL, so obviously it can't connect to WinHost because it's running inside WSL. So now we haven't loaded. Let's restart it. File hello serial.elf target remote WinHost 333. No, 333. And now we can disassemble/r this address. Yeah, it doesn't like it. So yeah, rev, that's the missing instruction. What does rev do? Probably bit reversal or something like that. And we don't have it, and we may need it, we may not. First of all, we can remove this. Let's see what rev does. Byte reverse word, reverse the byte order in a 32-bit integer. So I guess, yeah, it's just reversing the bytes. So the first byte and the last one exchange places, and then the two middle one exchange places. Nothing too fancy. Okay, so we have a bunch of missing instructions, and I think we would probably want to have them before we continue. And then there is like this reading from this address, which may or may not have anything to do with this warning, but I suggest, I think that before we implement this instruction, there is no way. I mean, it happens right before the panic, so there is a good chance it's somehow related. Yeah, I think if we implemented this and then those missing instructions, there is a good chance it will go past the panic. But for now, let's just commit what we have just done. Fix arbitrary or fit arbitrary 40, implement CMP register. That was CMP register encoding T2. CMP register encoding T2. And then we have still missing those instructions to do next time. So just like my previous very successful request, if anyone feels like adding those, I think they should be pretty straightforward to implement. I think rev doesn't really, where was that? Rev, not prevail. But I found it already. Where is rev? Rev. Yeah, so yeah, it doesn't really update the flags, and then there is like QXTH, which doesn't have to do anything with the flags as well, and there is like UXTB, which is similar and we already implement, and we have muls, which probably does have does update the flag. So but it's just checking if the result is negative or 0, and we have that code. So it shouldn't take a lot of time to implement this. I would say 15 minutes of coding plus maybe 30 more minutes to set up the environment and everything and write a test. So 1 or 2 hours if you are not very experienced with TypeScript and it's your first time. But please, if anyone has like a free hour and would like to just do us a big favor and implement those 3 for the next time and send me a pull request, that would be hilarious. I loved last time when it happened. And then next time we'll continue with the timers and what else? We had a document here. Yeah, we'll continue with the timers, and then we'll probably do USB or GPIO, and we'll just copy this list so I'll have it ready for next time. And then PIO, MicroPython, CircuitPython, the sky's the limit, you name it. Yeah, let's commit it and call it a day for today. So again, if anyone feels like you have this in the Git log now, the list of the instructions, so you can find it. I think we have it here. Yeah, wow, that's for 2 weeks ago. This tab is still open. Ooh, we did a lot of commits today. A lot of commits. Anyway, yeah, the new commit should appear in a moment. It's still pushing. GitHub is so slow today, or is it my internet? I don't know. Something is very slow. Anyway, so you have it. You don't have it yet. You will have it in a moment here. yeah, so feel free to implement. And yeah, I'm pretty happy with how this is starting to get somewhere with those peripherals, and we did a lot. We organized the code today, and it looks a bit better in my opinion, especially this. I really love this peripheral refactor. I think this is much more readable than the old UART that we had. It's deleted, but yeah, with all those read and write hooks, I think the new approach, I like it better. We still have a lot of work in front of us, but it's a good feeling to see this starting to work. So thanks Nekati and Che Guevaras and Tomasz and Steve and Pinti or Pintia, I don't know. Pronouncing names is always a challenge. Thank you for joining me today, and see you next week. And until then, have a great rest of the week. Goodbye.